In this video, we're going to be covering the E1 elimination mechanism in organic chemistry. So E1 stands for elimination unimolecular, which means that we only need one molecule, which is going to be the substrate, to start this reaction. Similar to SN1, this is going to be a two-step mechanism that involves a carbocation intermediate. But instead of the nucleophile attaching to the carbocation, like we see in SN1, we're going to have a base removing a proton and forming a double bond in our substrate. Let's look at what the general reaction form is. Before we look at the formula, let's look at the rate formula. The rate is just the substrate. All we need is the substrate, hence the unimolecular aspect of it. Like I said, this is a two-step reaction. The first step is the exact same as SN1, where we're going to have our alkyl halide with our leaving group. And the first step is the creation of the carbocation. So our alkyl group is going to become a cation, and it's going to separate from our leaving group, which will become an anion. The second step, I'll use actual elements here. So for step 2, what we're going to see is when we have our carbocation, we're going to have a base attacking the hydrogen of the beta carbon. The carbon that had the leaving group, the carbon that now has the plus charge, is the alpha carbon. The beta carbon is the one right next to it. And it needs to have a hydrogen available. Our base is going to attack the hydrogen. The hydrogen is going to give the 2 electrons that were in the bond and form the double bond. And then we're going to be left with our base with a hydrogen added to it, as well as a carbon-carbon double bond as our product. So let's look at some key features of E1 before we look at some examples. The first being that we get a carbocation intermediate. This is the exact same as SN1. We can also have rearrangements like hydride or methyl shifts in order to get a more stable carbocation. The order of stability is going to go tertiary, secondary, primary. We can't have methyl groups undergo E1 because we're going to form a carbon-carbon double bond. It's also important to check if we have any resonance happening, because resonance can stabilize the carbocation. So if we see something like a benzene ring or a double bond somewhere else, that can be a key indicator that we're going to have stability with our carbocation. The second key feature is that weak bases are enough. They do work on E1 reactions. If you remember the definition of a Bronsted-Lowry base, a base is essentially a proton acceptor. It just gains a proton. We have strong bases and weak bases, but since we have a carbocation, if it gets rid of that positive charge, if it gets rid of that proton, it'll become much more stable. It's really willing to get rid of that proton. So even a weak base can take that proton in order for our carbon-carbon double bond to form. Now the third key feature is that it uses polar protic solvents, exactly like SN1, and it's for the exact same reason. That protic solvents, polar protic solvents, have the ability to have hydrogen bonding, and they also have dipole moments. We have a partial positive and a partial negative side. We're going to have the partial negative side helping to stabilize our carbocation, and then we're going to have our partial positive side helping to further stabilize our leaving group anion. Now the fourth key feature is that it competes with SN1. They both share the carbocation step, and with these conditions, we're often going to see a mixture of SN1 and E1. One more important feature of E1 reactions is that it follows Zaitsev's rule, which basically means that the more substituted alkene will be the major product. Let's look at some examples. Here we have a tertiary carbon attached to a bromine. Our first step is our carbocation formation. Bromine is going to leave, become an anion, and then our tert-butyl group is going to become a carbocation. Now if we look at the second step, if we have ethanol in a solvolysis that is going to be reacting with our carbocation, we're going to have one of the lone pairs attacking one of the beta hydrogens. We should point out that it can attack any of the hydrogens on any of these carbons because they're all beta carbons. They're all one carbon away from the positive charge. But in this case, it's going to be attacking the hydrogen that's on the screen. The 2 electrons from the bond are going to go to this carbon-carbon bond, and that's what's going to form our stable structure. It's what's going to form our double bond here. What we're going to have is CH2 with our double bond to our carbon, and then all of our other methyl groups stay the same. And then our other product is our CH3, CH2, O, and now we have 2 hydrogens attached. And with one lone pair and these 3 bonds, our oxygen is going to have a plus charge. It's going to have to undergo deprotonation, which sometimes happens, and if it does, it's going to be a sub-step of step 2. It's not usually labeled as a step 3. What we're going to see is either another ethanol molecule taking that burden off, or what will eventually happen at the end, so I just like to write it from the beginning, is we're going to see our bromine from step 1 come in and take the hydrogen. And then we're going to have our 2 electrons going straight to the oxygen, making that a neutral molecule. And then we're going to end up with HBr as an additional product. Let's look at another example. Here we have Let's look at another example. Here we have an isobutyl group with a bromine attached. The exact same thing is going to happen where we're going to form a carbocation on the carbon that leaves, on the carbon where the bromine leaves. This is a primary carbocation, which is not very stable. We want to see if there are any rearrangements we can do in order to get this to a more stable carbon. Turns out, if we take this hydrogen and move it here and do a 1,2 hydride shift, the carbon that has the plus charge right now is going to become neutral, and then the carbon where it's tertiary will now get that positive charge. And a tertiary carbocation is one of the most stable carbocations you can get, so that's what we're going to rearrange into. If I redraw it underneath, we're going to end up with CH3 and another CH3 group and another CH3 group with our plus charge on the tertiary. Now let's have it react with methanol. This is another weak base. We're going to take one of our lone pairs, attack the hydrogen. The hydrogen is going to come off, give its electrons to form that pi bond, to form that double bond. And what we're going to see is the exact same structure, except here we're going to have a double bond that forms. And then our other product is going to be CH3O with 2 H's. Now again, we're going to have a plus charge here. We're going to have our bromine from the beginning coming in to take one of those hydrogens and deprotonate our methanol group. So then we get HBr as another byproduct, and then we regain our methanol to react again. Now I want you to take a look at this mechanism. After our carbocation formation in our first step, we're going to have 2 beta hydrogens, one being from this carbon, the other one being from the carbon on the end. To get our major product, which hydrogen would our methanol need to attack? It would have to attack the hydrogen, or one of the hydrogens, that's on the inside. The reason being is because we need to follow the Zaitsev rule. If we were to attack one of these hydrogens and form our double bond, well, we have one carbon that has no substitutions at all, and then we have another carbon that's only mono-substituted. Whereas if we formed our double bond here, this carbon is mono-substituted, and this carbon is also mono-substituted. So looking at our two options, the Zaitsev rule tells us that the major product is going to be the more substituted product. So that means that our major product is going to be the one that has two mono substitutions. So it's going to be CH3, CH, CH, CH3. This is going to be our major product or our Zaitsev product. Our other product will form just in much smaller quantities. So this is going to be our minor product, and that's CH3, CH2, CH with a double bond onto the terminal carbon. This is going to be our minor product, or what's called our Hofmann product. If this video did help you, please consider liking and subscribing. If you want to see how this compares to E2, SN1, or SN2, or see how all four of them compare against each other so you know which one to choose, all of those videos will be linked in the description. Thank you for watching.